Welcome students. Today we are going to discuss the important applications of infrared spectroscopy. There are many applications of infrared spectroscopy and we will be discussing a few of them. Apart from these applications which we'll be discussing here today in this lecture, there are many more applications which you can do. So let us begin and discuss some few important ones. Well, the first one is the identification of an organic compound. The identity of an organic compound can be clearly established from its fingerprint region, that is from 1400 to 900 centimeter inverse. The identity of an organic compound is confirmed if its fingerprint region exactly matches with the known spectrum of that compound. So if the fingerprint region exactly matches with the known spectrum of that compound, we are sure. The compounds containing the same functional groups may have similar absorptions above 1500 centimeter inverse, but they differ considerably in fingerprint regions. The next application is structure determination. This technique helps to establish the structure of an unknown compound. All major functional groups absorb at their characteristic wave numbers. Now the third application is qualitative analysis of functional groups. The presence or the absence of absorption bands help in predicting the presence of certain functional groups in the compound. For example, the presence of oxygen reveals that the group may be OH, C double bond O, COOR, COOH, etc. But an absorption band between 3600 to 3200 centimeter inverse limits the possibilities. The bend in this region may be due to OH. This region also speaks of absorption in case of NH2 and NH groups. In case of NH2, two absorption bends appear in the above region, while NH group gives only one bend. Its distinction from OH can be made from the extent of hydrogen bonding, which is stronger in OH compounds and causes more lowering in wave number. Then the next one, fourth one is distinction between two types of hydrogen bonding. This technique is very valuable to distinguish between the two types of hydrogen bonding. So this technique helps to distinguish between intramolecular and intermolecular hydrogen bonding. Now for example, orthonitrophenol exhibits intramolecular hydrogen bonding, whereas paranitrophenol exhibits intermolecular hydrogen bonding. Intramolecular hydrogen bonded compound does not show any shift in absorption or dilution, whereas intermolecular hydrogen bonded compound shows. So we can clearly distinguish between them. And the next one is quantitative analysis. So ion spectroscopy also helps to make a quantitative estimation of an organic mixture. The estimation of the components of a mixture can be done by first is measuring the intensities of absorption bands characteristic of each component. And second is knowing the optical density of the absorption band for a pure component. For example, it is known that commercial xylene exists is a mixture of three isomers, that is ortho, meta and para-xylenes. The separation of the mixture cannot be easily done. However, the percentage composition of the mixture can be determined by taking the IR spectrum of the mixture. Bends are seen at 740 cm inverse for orthoisomer and 880 cm inverse for meta isomer and 830 cm inverse for the para isomer. Mixtures of known composition are recorded and the working curves are drawn for the above bends for ortho, meta and para isomers. From the optical density values for commercial xylene, the percentage composition of each isomer can be calculated from the working curves. Then next one is study of a chemical reaction. So IR spectroscopy is very useful for studying chemical reactions. It is also used to predict the products formed in a photochemical reaction. Now let us study. We'll study this by the help of an example, the study of a chemical reaction. Consider the reduction of a saturated aliphatic ketone to form secondary alcohol. So here is the reaction. You can see butane 2-ol on reduction forms butane 2-ol. Ketone forms a strong band at about 10 centimeter inverse. When it is subjected to reduction, it forms butane 2-ol, which absorbs at 3300 centimeter inverse due to OH. The progress of the reaction can be studied from time to time, and the reduction will be complete when a strong band due to C double bond O will be missing and only a band due to OH is present. Now the next is the study of complex molecules. So IR spectroscopy is also useful to establish the structure of complex molecules. For example, two structures of penicillin were proposed on the basis of IR spectral studies. The first structure is beta-lactam structure and the second is oxazolone structure. The infrared spectra of oxazolones of the type show two characteristic bands, that is first one is 1825 centimeter inverse due to C double bond O, and second one is C double bond N, and that is at 1675 centimeter inverse. It is found that no such band appears in the spectrum of penicillin. Thus, the oxazolone structure for penicillin is ruled out. Now, it is known that beta-lactams do not absorb near 1770 centimeter inverse, whereas beta-lactams fused to thiazolidine ring exhibits a bend at 1770 centimeter inverse. Now, since penicillin gives a strong bend at 1770 centimeter inverse, the beta-lactam structure of penicillin is confirmed. So, we can easily confirm between the two structures of penicillin, that is beta-lactam structure and oxazolone structure, and clearly on the basis of IR spectroscopy, we can say that the beta-lactam structure of penicillin is a confirmed structure. Then the next one is the detection of impurity in a compound. Infrared spectroscopy is also useful in the detection of impurity in a compound by comparing its spectrum with the spectrum of the authentic sample of the compound. A pure sample always consists of sharp peaks and bends, while impure sample will consist of poor bends, and also some additional bands will be there in the spectra. Well, these were some of the important applications. There are some more like IR spectroscopy is also useful in determining the relative stability of various conformations of cyclic compounds. Well, one more is the geometrical isomerism. So IR spectroscopy also clearly makes a distinction between cis and trans isomers. Well, if we see rotational isomerism, then IR spectroscopy also helps in the detection of Gaussian skew and staggered conformations. So there are many important applications of IR spectroscopy. Thank you so much.